So we will continue to talk about the wind force estimate on marine structures. So in equation 2 we already said that the wind force normal to the surface can be computed by rho WA, where A is a projected area which is orthogonal to the wind flow direction, whereas PW is the pressure coefficient which can be pressure value which depends upon, can be computed from the equation number 1, and the coefficient of pressure can vary from 0.7 to 1.2 for cylindrical members. So wind will generate two kinds of forces, what is called the drag force and the lift force. One is parallel to the wind flow direction, other is normal to the wind flow direction. So half rho CD Vz square of projected area, which is half rho CL Vz square projected area. The only difference is the lift and the drag coefficient, which can be computed based on experimental studies. CDCL can be based on experimental studies, which is essentially a wind tunnel testing which is generally done to compute these values correctly. So this will lead to what we call what is acceptable wind spectrum, as we saw the load spectrum for aerodynamic loading. So the acceptable wind spectrum which is commonly followed in engineering practice for design of marine structures is actually the 1/7 power law, which says Vz is given by V10 Z by 7 power 1/7, equation number 3, where V10 is the velocity or the mean wind speed at 10 meters above the mean sea level. Z may be any value, any height above the mean sea level where you want to find the velocity. So since the exponential power here is 1/7, this law is called 1/7 power law. So this 10 meter is what we call as reference height. Now there is a very important comment which has been made on the power law by the literature. The power law which is being used as a wind spectrum for computing design forces on marine structures is basically an empirical relationship, and this holds good because this has a close agreement with the experimental findings. So this law is favorably being recommended by engineers for finding out the wind forces on members of marine structures. As I said, wind has got two components, which is the mean wind and the gust wind. This is the mean component, this is the gust component. This is static, this is dynamic in nature, this is fixed, this is fluctuating. So far we have been handling the mean component, which can be computed using the power law. Now how will you handle the gust component? Well, that is an important contribution. Now to find the load from the gust component, a gust factor is multiplied. to the sustained wind speed to get the gust wind. The average gust factor, which I call as Fg, as seen from the literature, varies from 1.35 to 1.45. Most importantly, the variation of the gust factor along the height is negligible, that is very important. You will see the mean wind component along the height is predominantly one of the varying parameter, it keeps on varying, but whereas the gust component does not vary with the height, it is negligible actually. Now the question comes, the gust component depends on the sustained wind speed. What should be the sustained wind speed taken for marine structures? That is again an argument. Okay. Various international codes advise different sustained wind speeds. So the sustained wind speed to be taken for design of marine structures is 1 minute average wind speed. As recommended by US Weather Bureau. So one must consider 1 minute average wind speed, you must measure the wind speed for an average of a minute and use that as your sustained wind speed to multiply this with the gust factor to get the gust wind in a design. You will also find another important term in the literature which is called fastest mile velocity. Now what is called fastest mile velocity? There is nothing but the gust factor multiplied by sustained wind speed. So generally a 100-year design wind with a velocity of 125 miles per hour is used for marine structures, that is important. So I use 100-year design wind speed, sustained wind speed with a velocity of 125 miles per hour to compute my sustained wind speed. So what I actually try to say is this: look at the 100-year record, look at the wind velocity of blowing at 125 miles per hour. During that scenario, take 1 minute average of the wind speed and use that value multiplied with the gust factor, which is given in the literature as it is, which will give you the gust component of your wind velocity or wind force. Interestingly, the design wind pressure, I am saying the design wind pressure on different components of marine structures, when the wind blows at 125 miles per hour is available in a tabular form which is given in the literature. Let us see what is that. These are the components this is the design wind pressure. Once you multiply this with projected area which is orthogonal to the direction, you get the force. So different components, the components are, let us say, flat surface, gusset plates, etc. Cylindrical members, mechanical equipments on the top side. So, some of the mechanical equipments will be cylindrical. So, we will say them as cylindrical only when their length is equal to 4 times of the diameter. In such cases, the recommended wind pressure which can apply onto these surfaces, which can be taken as the design wind pressure for marine structures, are the following. .87 kilonewton per square meter, 2.29 1.44. So, if you know the projected area which is normal to the direction of flow of wind, multiply these values on the surfaces to find out the wind forces on these surfaces respectively for design purpose in the marine structures. Now, let us quickly talk about the realization of wind on marine structures. Where is the complexity? It looks as if it is very simple, but there are some complexities in this, because we are seeing both the components independently, that is the mean wind speed and the gust component independently. So far we have been seeing, but in the wind as a phenomena they are acting together. So, let us see what is the wind speed or wind force realization on marine structures. Because there are two components. There are some important points. Wind and waves generally act together. So, we can say they are friends, whereas earthquake and wind, they do not act together. So, we should say they are orthogonal to each other. I mean this with the funny statement saying orthogonal means the product will remain 0. Therefore, wind induced vibration becomes very important for flexible structures. I should say compliant systems, because the moment structure becomes flexible, the structure will start responding to the wave action or the wind action. I address this as compliant systems in marine structures. Whereas earthquake forces becomes important in case of, I should say, fixed structures, but I would say bottom supported structures. You can have many examples like gravity based structure, fixed jacket platform, there earthquake forces will become important, whereas wind induced vibration becomes important in case of compliant structures. Let us quickly see some of the important parameters which are focused on wind force on structures. So, we will try to derive the aerodynamic admittance function, which is an intelligent representation of the random process of wind to compute the force on marine structures. There are some factors associated with wind forces on marine structures. We already know that wind has got two components, the mean wind speed and the gust component. Wind is a low frequency phenomenon. Wave is not. It is a low frequency phenomenon. The fluctuating component of the wind force is generally modeled probabilistically. Whereas earthquake forces are generally modeled by deterministic analysis. So, therefore, the behavior of marine structures in wind and earthquake are different in terms of two. One, how are they handled in the analysis? The way they are handled in the analysis, they are different. Two, the way in which they trigger the response. We have just now see here that earthquake forces, the way in which they act, or I should say trigger the response. That is, earthquake forces will become predominant when the structure is bottom supported. Wind force will become predominant when the structure is flexible or compliant. So, there are two effects of these forces on the behavior. One is by the way they are handled in the analysis, one is deterministic, other is probabilistic. The other is depending upon the support given to the structural system, is flexible, other is fixed. Okay. The moment I say probabilistic, then wind becomes a random process. It is very difficult to as it is model it in an analysis, because compared to earthquake modeling this becomes more complicated. So, how people have intelligently used this mechanism to make it simple, that is what we are now focusing. Okay. Now, the drag force on the members, the drag forces on members will be caused due to wind, will be caused due to waves. Inertia forces will be also caused due to waves. Inertia forces will also arise from earthquakes. What does it mean is that earthquake does not produce drag force. So, what does it mean? This statement implies a very important confirmation to me that vibrations induced on structures because of wind plus wave, wave plus earthquake are different. Now from this level onwards there has been a very serious idealization done by the literature. People said wind forces on marine structures are generally modeled or considered or handled in or as quasi static analysis. That is what many, and I should say most of the courts do. Additionally, when you got very slender members or slender structures as a whole, wind induced vibration are critical. This is also true for flexible structures. In my case, I will call this as compliant structures. Now, if we handle the same manner for wave action, this is for the wind action. Talk about wave action, there is a possibility that they may get cancelled. How? Look at the Morrison equation, look at the relative velocity term. If the structural velocity is phenomenally high in comparison to the wave velocity of wave water particle kinematics, then the net velocity to which a structure will respond to will become lower. So, there is a cancellation effect, but that does not happen in wind. Okay. This is what we call as de-amplification of response. This can take place in flexible structures in case of wave action, whereas in wind action, when the structure becomes flexible, the wind induced vibration will become more critical. Is that clear? So, it is very dangerous, or you must look at that with more care compared to that of wave action. Okay? That is what you are trying to say by the point number 8. These are some of the important critical factors which you must remember before you start estimating the wind forces on marine structures. Very simple, it has got two components, mean and gust component. We have looked upon them independently in the previous discussions. Wind is a low frequency phenomena, wave is not a low frequency phenomena. The fluctuating component of wind force is handled in the analysis or in the design using a probabilistic technique, whereas unlike in earthquake forces we do deterministic methods. So, the behavior of marine structures under these kinds of forces, that is wave, wind and earthquake, they are different in many forms, many manner. One, the way in which they are handled in the analysis. Two, depending upon what force will trigger what kind of structure is also important. So, with this context, look at this point. If you have a very slender structure or slender member in a structure, we all understand what is slender member. The length of the structure is very, very long compared to the cross sectional dimension, therefore, the radius of gyration becomes very small in that specific axis of bending, therefore, structure will start inducing vibration on its own even under small magnitude of forces of lateral action. Okay, that is what we call as slender members, or you have got a slender structure. In that case, considering wind, it is very critical because it can induce vibration, it is called wind induced vibration, whereas for waves are concerned, they have an action of, they have a category or capacity of even de-amplifying them, they get cancelled. Okay. So, they behave differently, that is what we put here. And interestingly, wind and wave both can cause drag forces, whereas earthquake cannot. Wave and earthquake can cause inertia forces, wind cannot. So, let us categorically understand before we estimate this. Now, the question is how this fluctuating component which is probabilistic modeled is handled along with the with the mean event component in the force calculation. That is what we are looking at now. Okay, so I need a function which can transform the fluctuating component to a static component to make it easy to handle in my analysis. Okay, that job is done using aerodynamic admittance function. Now let us say I want to consider wind as a dynamic process. If you want to consider wind as a dynamic process, then what are those factors which are important? To qualify wind as a dynamic process. 1. Length of the record. How long is your record? There are many ways of observing wind forces or wind pressure on any body. One, you can have a continuous recording. So, the record length can be very long. For example, let us say throughout the year, throughout the day you got many number of records. So, the record length can be very long. The second process can be you can record intermittently, that is every 1 hour interval you record, let us say 8, 9, 10 am, 11, 12, like every 1 hour interval you record, that is called intermittent recording. The third can be you keep on monitoring the wind velocity. If the value exceeds any threshold value, then record it. It is called conditional recording. So, keep on monitoring it. If the value exceeds any threshold value, maybe 30 miles per hour, 100 miles per hour, the threshold value is fixed by the code. If your velocity during the day, during the year, during the month, if it exceeds, one mark is given. So, keep on, that is called conditional record. Now, very easy. If you got a long record, the average will be very low, is it not? The denominator is higher. If you got an intermittent record, the average will be high. So, depending upon the process of the length of the record, you will land up in a variation. Okay, you can say my wind velocity is higher, one can say wind velocity is lower, depending upon by what method you have recorded it. That is what we call as length of record. All these are dynamic in nature because all these are varying with time. Okay. Now, the second aspect is averaging time. It is actually the time at which the record is averaged. Now, thirdly, the wind spectrum becomes an input for the analysis. So, the dynamic component or the fluctuating component should be also considered. Strictly speaking, in probabilistic modeling, this kind of component can be considered using what we call cross spectrum. Equivalently, this can be considered by deploying a new function called aerodynamic admittance function. Now the fundamental question comes, before we understand what is this function, the fundamental question comes, what would be the advantage of using an aerodynamic admittance function in place of a cross spectrum or in place of a fluctuating component. There are two advantages in this. A, the foremost advantage is you can bypass the rigorous random process. Two, the aerodynamic admittance function can be evaluated using experiments, that is very important. That is, you can always quantify them easily. So, if you are able to quantify them easily, why we should go for a complicated phenomenon? Okay. So, the aerodynamic admittance function is actually substituted for the fluctuating component because of two reasons, that I can easily bypass the rigorous random process involved. Secondly, this function can be evaluated actually using experimental conduct, that is in wind tunnel testing we can do this and find out the aerodynamic admittance function for different bodies of different shape, different height, different spatial distances. I can do this, okay. I can find out these functions easily on any surface of a body. So, therefore, now we are inclined to understand how this function looks like, how this is plotted, how it is being used. Let us see V of t is equal to half rho C d dia u dot and u dot. This is for the drag force as far as wave is concerned. Half rho w C w projected area, I should say V t square, this is for the wind is concerned, is it not? I expand this half rho C w a V plus V of t the whole square. So, the mean velocity, mean wind and the gust wind. So, half rho C w a V square V of t square plus 2 V bar V of t, okay. It is very important to note that V bar mean wind velocity is much higher than the gust component, okay. In that situation this square can be made to 0, okay, we can neglect this. So, I can rewrite this equation which is force due to wind I will do this later. Now it can be written as half rho C w a V bar square plus rho w C w a V bar V. So, I call this as steady mean drag force which is indicated by Fw, the bar above indicates me it is the mean value, other is the gust component which I call Fg, of course the function of t. I will call this equation number 5. So, let us say I have a single degree freedom system model when the model, and this model has the projected area A, that is projected area as A. Now the response, okay. The response will have a static component, then we will have a dynamic component, okay, which will vary within this. The static component can be easily indicated by Fw by K, where Fw is the static mean drag force here, which we call as a static displacement, x static displacement plus the vibrating component, which is called the dynamic response. I call this as DFT. One is the static value, other is the fluctuating component or the dynamic component, which is DFT. Now here there is a need to handle DFT. Here there is no problem for the static component, we are worried about the dynamic component. Now how this is handled? Assume that the wind force is, or wind load is an ergodic process. We already saw in the last lecture what do you mean by ergodic process. Ergodic process is that single sample from the ensemble of different time histories which has got the mean value as equivalent to the classic value of the whole ensemble. It represents the ensemble in an indirect form. Okay. If this is agreed upon, then DFT becomes a single signal. Some process, single, which is an arbitrary time history. Once we agree that this approximation is valid, why this is valid? Because we are assuming the wind load has a ergodic process. Once we agree this process as ergodic with this approximation, the one sided power spectral density function of the wind load is related as below. The wind force is related to the Gus component square of the wind velocity or the velocity spectrum. This is true when the process is idealized as an ergodic process. We call this equation number 6. Already in equation 5, if you turn back, you have this Gus component ready, that is called Fg. What is the component? The Gus component is already seen in equation 5. That tells me that can be related now to rho CD A V bar square. Is that okay? Because multiplied with Vt is what we have with the Fg value square with that of the wind velocity spectrum. Now interestingly, in the same equation 5, V bar can be also obtained separately because Fw component is there. Substitute back for V bar separately because we already know that Fw or F bar W is half rho V bar square, is it not? So what I want to do is I pick up V bar square from this equation, substitute back here and get my equation modified. If you do that, my force will become 4 F bar square by V bar square of, is that okay? I call this equation number, this is 7, equation number 8. Now in case of marine structures, equation 8 can be conveniently modified using aerodynamic admittance function. We will see how it is modified. First let us see why it is possible. It is possible because marine structures have large bluff bodies. and they are massive. Because of these two characteristics, you can always replace or handle this equation 8 using an admittance function. Now we will see how. Why I have seen, how I will see now. I will remove this. Now the right hand side of the equation 8 is modified with a new function which I call chi function of square of this. So now my force spectrum will become 4 equation number 9. Let us quickly see the characteristic of this function. I try to plot this function as a variable with a, because in this case projected area, wind velocity or the mean velocity are all fixed values. Okay. The only variation is omega. Let us see how the admittance function varies with omega. Try to plot that. This is omega, this is chi of omega, this value is 1. So this figure implies that when omega root a by 2 pi v bar is 0, when it is 0, a cannot be 0 because area has got a projected area, it cannot be 0, wind velocity can never be 0. Okay. So the only possibility is omega is 0. In that case my chi of omega root a by 2 pi v bar becomes unity. When omega root a by 2 pi v bar becomes infinity, that is very large, then my chi value becomes 0. That is what I infer from this figure. That is the behavior of the aerodynamic admittance function as a function of frequency. Okay. Remember, fluctuating means what? Frequency dependent, that is what fluctuating is it not? I am handling that here actually. Okay. I am taking care of that fluctuating component with a function which takes care of this, of course with this idealization. Now I can multiply this function directly in the spectrum to give me force output if I know the velocity spectrum. Okay. So the fluctuating component which is a function of frequency, which is a probabilistic modeling element, is transformed to a methodology like this, which is comfortable to handle in this case. This is what we call as aerodynamic admittance function. Now how literature qualify this function? Okay. How this function can be evaluated? Experimentally you can evaluate this by conducting experiments in wind tunnels We can evaluate this. How? You have to evaluate this. If you have a bluff body, work out the projected area, work out the velocity, mean velocity attacking the bluff body. For every frequency keep on plotting this, you will be able to get the chi value, okay. But analytically also literature suggested that chi value can be handled using the equation given by Davenport. Davenport suggested the aerodynamic admittance function as any value or any variable of x can be said as 1 by 1 plus 2x to the power 4 by 3, that is given by Davenport, whereas in my case x will be omega root a 2 by v 1, okay. I can plot this. I call this equation number 10. So, we have understood now in this lecture how to handle wind forces on marine structures, be it flexible, be it fixed, or be it rigid, be it compliant. And wind has got two components, one is the basic wind speed or average or mean wind speed, other is the gust component or the fluctuating component. We have understood how to handle both of them using the power law and the fluctuating component using the admittance function like this. So, one can easily able to find out what would be the force spectrum on a given member of a marine structure if I know the velocity spectrum, okay, using the aerodynamic admittance function. This can be generally evaluated using experiments, but analytically also you can evaluate this by suggested by Davenport. These are all suitable and closely applicable only for marine structures. Why? Why it is so? Because they are all averagely worked out at 1 minute average speed for 125 miles per hour for 100-year return period, okay, as suggested by US Weather Academy. Okay, that is how we have handled, we have learnt how to handle the hydrodynamic loads on marine structures, how to handle the aerodynamic load on marine structures, how are they different, why are they different, where are they different, how are they handled. Now we will in the next lecture talk about the ice loads and earthquake loads, and we will summarize all the 4 components of loads. There are other loads also, but these are major components acting on the marine structures. Once we understand them, we started designing and understanding the ultimate load design methodology for marine structures. Once we understand that, we will move on to plastic design of marine structures. Is it clear? Okay.